so much, Michelle, for that very, very gracious and informed introduction. I really appreciate it. You can all hear me? Great. Okay. So the first two lectures will be about differential privacy. Today's lecture is really intended for a very broad audience, and I will point at a few different things that we will go into in more depth tomorrow. Yes. Good. So the title for this series is Mathematics and Mores, and just for the non-native speakers, I wanted to just give the definition of mores as the fixed morally binding customs of a particular group. Notice that it doesn't say what is right and what is wrong. It's not the same thing as ethics, but it's contextual. And that will be particularly important when we get to fairness. This is part of a theme for me. I really, really believe that theoretical computer science can be a vector for positive societal change. And I think that all of us could work in that direction. So let me say a little bit about privacy in a nutshell. When we think about privacy-preserving data analysis, there sort of are two kinds of things that we might think of. One of them is somehow the statistical understanding of the population as a whole. For example, as we do with the census data, or as we might do if we're trying to analyze the history of loans, looking for evidence of discrimination, or even coming up in machine learning where we're trying to train an algorithm to distinguish cancerous cells from non-cancerous cells. Or in machine learning, maybe you have access to text that people spoke because you're doing some kind of natural language processing. So privacy is more obvious an issue in that case. So this is one kind, statistical understanding of the population as a whole. The other kind is the sort of needle in a haystack, as exemplified by the so-called total information awareness system that was designed supposedly to find terrorists. Okay? Now, differential privacy is for the first kind of task. If you're trying to do some kind of privacy-preserving, find the needle in the haystack, this is the wrong tool for you. I don't know what would be the right tool, but I want to be very clear that we're in the tasks on the left, not the one on the right. Okay. So statistics. A statistic is a quantity that's computed from a sample. And statistics feel private. Why would they feel private? Well, two data sets that are collected independently from the same population with the correct methodology really ought to tell us essentially the same thing. This is why the field of statistics works in the first place. If by doing two good random samplings you got very, very different outcomes, then something is wrong with your statistics methodology. You can't really infer things about your population as a whole. And so I think that the sense of privacy comes from exactly that fact. For example, people may say to themselves, no one knows I'm in the sample. I could have claimed that I opted out. Or what is learned really isn't about me because the same things would have been learned even with a completely different sample in which I didn't appear. Now, so you might say, let's just release statistics, whatever that is. When you have some intuition what a statistic is, and then everything is going to be fine. And oddly, that fails completely, but it is also at the same time on the right track. And so it needs some help, and differential privacy will provide exactly this help. In fact, differential privacy will maintain the I could have opted out semantics, even if we're looking at a total population count. So the same semantics of I could have opted out, even though we know that it's supposed to be a total population count, meaning we count everybody. Okay. So how do we abstract the general problem of privacy-preserving statistical data analysis? We imagine that we have a database here on the left that has lots of really good, juicy information that's also very sensitive. And we have a data analyst. And in this very high-level abstraction, the data analyst asks questions or makes queries to the data set and gets answers. And then depending on that answer, the analyst chooses the next question. So it can be an adaptive process in which the ith question that's asked depends on the I minus first answers that were observed. Now, this is really, really abstract. So for example, a query could be, tell me how many people in the data set satisfy some property. Or it could be, give me the following tables. Or it could be, let's run a study on the heart database from Framingham. And then I'm going to publish the results of my study. So the first query is, run all these analyses and do all kinds of thinking and now publish the result. And then the next study may very well depend on what was found in the first study because people wish to follow up on something. So it's just extremely broad. And the query could also be, give me a synthetic database that in some sense looks like the real data, or tell me everything you know. So we have to be able to answer all of these things. Now, our driving scenario when we were first thinking about this was the US Census Bureau. First of all, census data is the data of the people used in part for allocating the people's resources for the benefit of the people. So we really liked the mission, but also there's a law that says you have to maintain privacy for the respondents. So it wouldn't just be a situation of push, it would also be a situation of pull if we were successful. Okay. Now, the question of how do you survey people in a privacy-preserving way that allows them to answer questions comfortably about sensitive things like drug usage and so on is really old. And tomorrow we'll probably see an example due to Stanley Warner from 1965. Okay. So let's use flossing as an example of a sensitive query. And we're interested in knowing questions about what fraction of some set of people floss their teeth regularly. Okay? Little sensitive. So if you just think of statistics, you might ask the question, how many people in the House of Representatives floss regularly? So suppose, and this seems like it's a pretty vanilla question and answer, right? If you get the answer to this, if it's unanimous, maybe you'll draw some conclusions. If it's zero, you can draw conclusions about individuals. But if it's somewhere in the middle, your feeling is probably that you don't know who flosses and who doesn't floss. And that's basically true. But suppose we asked a second statistical query, a query about a large set of people. How many members of the House of Representatives other than the Speaker of the House floss regularly? If you have the exact answers to both of those queries, you know whether or not the Speaker flosses regularly. So this is called a differencing attack. And, oh, okay, great. So a differencing attack is just one example of how seemingly innocent or innocuous queries over large sets of people can be combined to compromise privacy. But generally, more generally, there's what we call the fundamental law of information recovery or fundamental law of information reconstruction, which says that overly accurate estimates of too many statistics completely destroys privacy. And the definition of overly in overly accurate is tied to the definition of many in too many. And a good analogy might be to the cumulative effects of radiation. Small dosages of radiation can add up to cancer-causing exposures. And the effects are cumulative, and the same is true with privacy loss. Moreover, you can safely have more dental x-rays in a year than you can have mammograms. Dosage matters. Too many is related to the degree of accuracy. So that's kind of the backdrop that we're working against. Overly accurate estimates of too many statistics is blatantly non-private. Now, we next have to turn to definitions, because without definitions, we literally don't know what we're talking about. This is Cecilia Payne-Gaspardin. Is anybody familiar with her work? She was the first woman ever to receive a PhD in astronomy. She was also the first person at Harvard to get a PhD in astronomy. And she is famous for estimating the amount of hydrogen in the stars and determining that it's much greater than the amount of hydrogen in the Earth. So her research contradicted the prevailing view, correctly contradicted the prevailing view that the stars and the Earth, or the sun and the Earth, have the same composition. Okay, so here she is. She's in our data set. And the question is, what would we like to offer her as a privacy guarantee? What should we say to her? So one thing you might say is, you can't learn anything new about Payne-Gaspardin that you did not know before. So notice that we don't say you can't learn anything about her at all, because, well, you know, there may be lots of information about her that's out in public. She may be a celebrity. She may be an extrovert. But somehow, what Tordelinius proposed in 1977 for a statistical data set is that interacting with the data set shouldn't teach you anything new that you couldn't find elsewhere about this person. How many people here are familiar with semantic security for a crypto system? Very similar, right? Seeing the ciphertext doesn't tell you anything you didn't already know about the plain text. Okay. The problem is, unlike in eavesdropping on communication, the whole point here is to actually learn something about your data set. If you can't learn anything about your data set, then what is the point of a statistical database? So, for example, suppose I'm from Mars, and I believe that all humans have 2 left feet. And I learn as a result of a statistical analysis through a privacy-preserving database that the vast majority of people have 1 left foot and 1 right foot. My beliefs about Payne have changed. Before, I believed that she had 2 left feet. And now I think it's pretty likely that she has 1 left foot and 1 right foot. I have learned something about her that I didn't know before. And the question is this a privacy violation? Well, we're making up the definition, so we get to decide. We said no. Why? What's the intuition for saying no? Well, ideally, we would actually learn the same things if Payne was replaced by Henrietta Swan Leavitt. Henrietta Swan Leavitt was another astronomer, and she was famous for determining a relationship between certain variable stars' peak brightness and the period over which their brightness varied. And this turned out to be a valuable means for measuring distances across space. So the point is, we would learn the same thing about Payne's feet, even if Payne left the database, Payne was replaced by Leavitt, or other small changes were made to the database, right? And so in that sense, it isn't learning about Payne, it's learning about people as a whole. And we simply declared it not to be a privacy compromise. And that brings us to the English language definition of differential privacy. It says that the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. Okay. So if you study that carefully, notice that I didn't say anything about who knows what. So even if our data analyst, who could also be our privacy adversary, even if our data analyst knows the whole database and knows all about Payne's data as well, and knows that you're operating on one of those two databases, even so, seeing the outcomes should not tell the adversary which of the two databases is the actual database, because the outcome of any analysis is essentially equally likely, independent of which of the two databases we're using. Yeah. I can reattach. Let's try this. Is it okay? All right, thank you. So again, an adversary knowing both data sets in their entirety will never be able to distinguish. So the question is, what is the source of uncertainty when we say essentially equally likely? Where is that likelihood coming from? It's not over the choice of the data set. It's over randomness that is introduced by the algorithm. So our algorithm is going to flip some coins, and that's where the uncertainty is coming from. Once the algorithm flips coins, if you fix the database and ask a question, you get a probability distribution on outcomes. And so what we're asking is that the probability distribution on outcomes, when the databases are very similar, should themselves be very similar. So just to drive the point home a little bit more, suppose I have two coins. I have a fair coin and I have a slightly biased coin. Okay? If I'm given one of these coins, the flipping algorithm is going to produce either heads or tails. And the probability distribution on the outcomes is nearly identical for the two different coins. So given one or even several flip outcomes, nobody can ever, with any decent amount of confidence, determine which of the two coins is being used. And that's the same thing that we're using in differential privacy. It's exactly analogous. So what I've been describing is a kind of stability condition. The distribution on outcomes is essentially the same, even if I perturb the data set a little bit. The stability is preserving Payne's privacy. But it turns out it's also preventing overfitting. So it's well known that generalizability in machine learning requires some kind of stability. If your algorithm isn't stable, you won't be able to generalize. And in fact, we're going to see that differential privacy also not only gives privacy, but also gives a way of preventing overfitting, and we'll talk about that tomorrow. So it's a defense against p-hacking. And while many people think about an inherent conflict between accuracy and privacy, what we're seeing here is that a different kind of accuracy, the ability to generalize, is in fact really aligned with privacy. Okay, so we've done the motivation and the English language definition. Here's the formal definition of differential privacy. I don't know why it advances. Okay. So first of all, our algorithms are often called mechanisms, and that's why we're using the letter M. Differentially private algorithms are equipped with a parameter that, roughly speaking, bounds the privacy loss. And we need one more definition before I can explain this to you, and that is the notion of adjacent data sets. So two data sets, X and Y, are adjacent if they're almost identical. In fact, one of them is a subset of the other, and the larger one has the data of just one more person. So everybody in this room versus everybody in this room except me. And given this notion of adjacency, and notice I didn't say which of X or Y was the largest one, we're going to require that for every possible output event, outcome event, when the algorithm operates on a data set, the probability that we observe this event when the algorithm is running on database X is at most e to the epsilon times the probability that we observe this event when the database is Y. So we're bounding this ratio, just divide through by probability of CS on M of Y. And since the roles of X and Y are symmetric in this definition, the other inequality has to hold as well. Okay. And we call epsilon a bound on the privacy loss. And again, the randomness, when we have probabilities, the randomness is over the randomness of the algorithm. And when epsilon is small, this is about 1 plus, e to the epsilon is about 1 plus epsilon, so you can see how these things are very similar to each other. Okay. Notice that the statement is about the behavior of the algorithm, M. It doesn't care who knows what. It doesn't even care what somebody may learn in the future, as long as they don't learn specifically, which database did you use of the two that I thought you might be using? But anything else that they learn about the people in the database from other sources, completely irrelevant. Membership in the database can be extremely sensitive. For example, if it's known to be, say, a database of alcoholics. So this is a non-trivial guarantee. It's important. So differential privacy separates what is learned about the individuals in the data set from the teachings of the data set, from the teachings of the data, as opposed to what is learned as a result of somebody participating. Because the same teachings will happen with almost the same probabilities whether one chooses to participate in the data set or not. So this doesn't say that no harm can come to anybody. It just says you won't get any extra harm by choosing to participate, or very little extra harm, risk of harm, by choosing to participate. So what's one kind of harm? One kind of harm might be the following. We have a database, it's a medical database. We learn from it that smoking causes cancer. It's known that, let's say I'm a smoker, I'm not, but suppose I've learned that I am, then my insurance rates will go up, right? I'm harmed. On the other hand, learning that smoking causes cancer is the whole point of medical research, because it teaches people that they should stop smoking, and maybe I will now enroll in a smoking cessation program. So we like science, we like learning, we like machine learning, and this is what we want to be able to continue to do. Okay. So let's go back to our learning about the population as a whole versus learning about the needle in the haystack. if you have two data sets, X and Y, where X is, the haystack, and Y is the haystack but without the needle, you shouldn't be able to determine which of the two data sets is actually being used. The behavior is essentially the same. So we are hiding the presence of the needle. And that was actually really central to our goals. We wanted to hide the outliers. The motivation for that is that the outliers are often the people who most are in need of privacy protection. The people who are absolutely typical and just like everybody else may not need privacy protection. Okay, now there are some properties that flow from the definition of differential privacy. First of all, it's future-proof. That is, it's resilient to present and future information that comes from other sources. Learning later more things about the people in the data set or maybe not in the data set cannot help you to figure out what happened when you got a differentially private release of some information. Also, crucially, differential privacy composes gracefully and automatically. So we can understand, just like with those X-rays, the cumulative risk, we can understand the cumulative privacy loss over multiple computations. At worst, the losses add up, but we'll be able to think in much more interesting terms than just addition. What that means is that differential privacy is now programmable. That is, we can define small differentially private primitives, and we can put them together in creative and interesting ways in order to carry out more complex privacy-preserving statistical analyses. And just as algorithm design takes sort of conceptual building blocks and puts them together in creative ways, this is exactly what's going on in the field of differentially private algorithm design. In addition to trying perhaps to minimize space and time, you will also try to minimize cumulative privacy loss. So here's a simple example. There are many differentially private algorithms. There are several primitives. But here's a simple example, which is symmetric noise addition. So maybe you want to know what's the population of Washington, D.C. And you look at some numbers from the census, and they estimate the population in Washington, D.C. on July 1st, 2017 as 601,723. Now, how would you get this information in a privacy-preserving way? Well, if somebody opted out, this would move the count to 601,722. And so what we want to do when we add random noise is we want to sort of hide the presence or absence of that one person. So we want to add noise that is, maybe it's symmetric. I mean, we're going to add noise that's symmetric, but what you observe should also be observed with pretty high probability, even when the data set has a count of 601,722. So how fat should these curves be, right? Well, you only want to hide one person, so it has to be at least kind of one wide. And I should mention, we're going to use delta to represent what we call the sensitivity of the function. That is, it's the maximum amount by which the value of the function can change when one person opts in or opts out. So worst case over all pairs of adjacent data sets. So the sensitivity of a counting query is just 1, because if one person opts in or opts out, that can change the count only by 1. But we're also interested in restricting the privacy loss. And so we want to have less privacy loss when epsilon is small, or we might be willing to be permissive and have epsilon, the privacy loss bound, be large. So the right answer is going to be of this form. We're going to add noise that somehow its fatness looks something like delta over epsilon. Delta's in the numerator, so if you have a function where changing the database by one person really swings the value of the function, you have to fatten up that noise. Similarly, if you really care about privacy, you want to, again, to have the noise spread things out. And so we have epsilon in the denominator. Small epsilon means a bigger value. And the right distribution turns out to be the Laplace distribution. And the proof is so straightforward, we should just give it. So suppose you have some function f that you wish to compute that operates on databases, which are subsets of our universe, and it's a real-valued function. Again, delta is the sensitivity of function. It's the worst case over all pairs of adjacent data sets on how much the addition or deletion of one person can swing the value of the function. And so the privacy-preserving solution is to add noise from the Laplace distribution with parameter delta over epsilon. And this is the probability density function. So our B here is the parameter delta over epsilon. And why does it work? So here I have a database Y, and this is f of Y. And here I have a database X, and this is f of X. And these two curves show the output distributions on the two different data sets. And let's look at some particular outcome T. And we need to bound the probability density at T in these two different distributions. So just plugging in this value, the two B's will cancel out, so they go away. And what we get is the density at T here is e to the f of x minus T over B. And over here, it's e to the f of y minus T over B. And then we use the triangle inequality in the superscripts, in the exponents. And we get, this is bounded by, oh, you can't see this. Sorry. Pointer. So this f of x minus f of y in absolute value, that's bounded by the sensitivity of the function. And so that's our delta here. And then our parameter b is delta over epsilon, and the deltas cancel out. OK. So I've been talking about epsilon differential privacy. And when we started doing this work, we said, well, epsilon, it's a parameter. You get to choose this. You as the database administrator, you as the regulator, you as the CTO get to decide what's the right value of epsilon. And what do you think the first question was every single time we presented it? What should epsilon be? Right? It's like, it's such a foreign concept. And I wish there were a really succinct answer, but let me just tell you a little bit about it. First of all, a small epsilon is a happy epsilon. It doesn't matter what the algorithm does. If epsilon is small, very little privacy loss, and that's good. And when I think of small, I usually am thinking of like 1 in 100, maybe 1 in 10. Certainly try to keep epsilon below 1 if I can. OK. All happy epsilons are alike, but an unhappy epsilon is unhappy after its own fashion. So some high epsilon algorithms are just awful. And some of them might be lucky, especially if it's used in isolation just once. Okay. But nothing ever is used in isolation. You're giving somebody a power tool, and they just want to have at it. And they want to do all sorts of things and ask all kinds of questions and all sorts of analyses. Nothing is ever done in isolation. Okay. So how do we cope with it? If we drive epsilon way, way down so that when we do lots of things, it doesn't add up to too much, that might just put in too much noise and make everything really crazy looking and useless. Although it's very interesting to consider problems in statistical inference in the presence of really nice noise that we understand. There actually are things that you can do. The other thing that people do is they relax the definition of privacy. And we will see several examples of that. So they'll relax the strict, guaranteed absolute bound on epsilon and allow privacy loss to be larger with some small probability. So we'll talk about those ideas tomorrow. They also develop so-called amplification techniques, which just are little twists you can do on algorithms to make them all at once more privacy preserving, although it can, depending on what's going on, it can cause a hit in the accuracy, but not always. So we'll see examples of that. Now, another comment. Suppose we're running on, we're running either on X or Y. Suppose the truth is X. If we run the algorithm on X and we come up with a response, an outcome, that's more likely when the database is X than when the database is Y, that, as you'll see, gives us a sort of a positive privacy loss. We really have lost something. We've tossed out this breadcrumb that's actually aiming in the right direction toward X. But we might very well, we will, sometimes, output, even when we're running on X, we'll still output values that are more likely when the database is Y. When that happens, when we formally define privacy loss, we'll have a negative privacy loss. So privacy loss can be positive or it can be negative. It is more likely to be positive, but it is pretty likely, depending on the algorithm, also to be negative. And what do you think when you see something like that? Cancellation. When these epsilons are adding up, there's also going to be a lot of cancellation. And that's going to help a whole lot. And we'll see some of that tomorrow. So this just gives you a little taste of what some of these definitions are going to be. Concentrated differential privacy very roughly says that the privacy loss itself is sub-Gaussian or is Gaussian. So for all k, the probability that the privacy loss will exceed k times epsilon is 1 over k e to the minus k squared over 2. So you can compare that. It's quite different than saying the probability of exceeding epsilon is 0. But still, you exceed epsilon, but you're very likely, if you exceed it, to just still be at 2 epsilon at most. And super likely to be within 3 epsilon, and so on and so forth. So it may not be so bad. And in fact, this notion, cleaned up by Bunn and Steinke, is the variant that is used in the 2020 US decennial census data. So that brings us to the rest of the title of the talk. We've talked about differential privacy. Now we're going to talk about the US Census. So differential privacy is now widely used in industry. It's used by Google. It's used in every Apple device. It's used by Microsoft, by Uber, and so on. But it's not used comprehensively, even by the companies that make the most public emphasis about their dedication to privacy. The census is completely different. So most of you probably know this, but just in case, every decade the US Census Bureau completes what is supposed to be a complete enumeration of the public. And based on those numbers, representatives are apportioned in the House of Representatives. And over $1 trillion of funding is allocated. So it has a huge impact. It's also used in, although unfortunately less and less, in the enforcement of civil rights, such as the Voting Rights Act, information about the demographics of areas. Okay. The Bureau releases about 7.7, well, in 2010, they released about 7.7 billion linearly independent statistics on the data of about 300 million people. Remember what I said about overly accurate estimates of too many statistics? We are definitely in the too many area, right? And what the Bureau did was, I talked to you about the fundamental law of information reconstruction. The Bureau carried out a reconstruction attack on the data that it had, on the statistics that it had released in the 2010 census. And I'm not going to go into the details, but here's a quote from John Abad, the chief scientist and associate director of research and methodology at the census. These technical advances revealed a new vulnerability, allowing people to reconstruct data from tables that were previously assumed to be privacy preserving. So the Bureau said, we need to do something about it. Now, a lot of people will say, decennial census, that stuff isn't very private. Who cares, you know? My neighbors already know that this is a same-sex household. But the worry is something like weaponization of the census data. Yeah, your neighbors know that you're gay. This is the neighborhood that you chose to live in. If arbitrary people anywhere in the world can figure out, can get a list of all of the gay households in the country, that suddenly feels very, very different. Another kind of thing that can be compromised here is people in public housing, Section 8 housing, may be living in violation of their lease agreements. More people living in the home than are supposed to be living there under the agreement. These people risk eviction after having perhaps waited years to get public assistance, public housing. Here's a new one that has come up. Your 13-year-old daughter, 10 years ago, you had a 3-year-old son. In some states, this will make you vulnerable, at risk, for prosecution for child abuse because you are supporting gender-affirming care for your child. So the risks of these sort of seemingly simple things can be great. Okay? Now, there's another kind of harm also. So usually, people draw a curve that looks something like this. We have privacy on the x-axis, less private is over here, more private is over there. Utility on the y-axis, less useful is here, better utility is up there. And the cartoon of the curve, says, gee, we have great utility if we have no privacy. And we have no utility if we have perfect privacy, and we're looking for a sweet spot. I question this claim that if we have no privacy, we'll have great utility. It may be true now, but if you do something like this and you have a serious weaponization of the census data, then people won't answer next time. And you will have no utility in the future because you're not getting respondents. So there's a time element that's missing from this picture, and you'll see this picture all the time. Okay. So what did the Bureau do? The Bureau decided to use differential privacy, and yeah. So what happened? Privacy became political. So the state of Alabama filed a lawsuit against the US Commerce Department. Commerce runs the census. Challenging the Bureau's announcement that it will be delivering redistricting data to all states by September 30th using differential privacy. And it was joined by several other states. Alaska, Arkansas, Florida, Kentucky, Louisiana, Maine, Mississippi, Montana, Nebraska, New Mexico, Ohio, Oklahoma, South Carolina, Texas, Utah, West Virginia. So Maine and New Mexico have Democratic attorneys general. All the other states have Republican ones, and all the other states are red states, like red legislatures. So I did not expect this. I did not anticipate this. Neither did the judges on the three-judge panel who were listening. And one of them actually said to the plaintiffs, what's going on here? Is this rural versus urban? Is this Republican versus Democrat? Tell me the truth. So the court rejected Alabama's challenge, and that judge actually accused the plaintiffs of shape-shifting. We expected this to be appealed to the Supreme Court. It was not, possibly because the language in the decision was so strong. But this is not over. So these are the redistricting files. These are what's used for apportionment to the House of Representatives. These numbers, that's the first thing. For Voting Rights Act cases, other numbers get used. For allocating funds, other numbers than just the first set get used. And we're going to see what happens. We just don't know. So just a couple of remarks. This is my last slide. Privacy noise has actually been added since 1990. So in differential privacy, the Bureau said, we're adding noise, and this is how we're doing it, and here's our algorithm, and you can look at it. So with differential privacy, the entire methodology is public. Only the actual random values that are drawn from the distributions are kept hidden. The noise that was added in the past was done through various means, principally something called swapping, where households that are very unusual within their census block may get swapped outside to another census block, another census tract, another, I don't know if they cross state bounds, I forget. Okay, there are also undercounts, always. Children are undercounted, poor people are undercounted. Undercounts were exacerbated this time by the pandemic, and things really got confused because, say, you had students who normally would, remember that the census day is April 1st. April 1st, 2020, a lot of students who normally would have been in university were home. They were scattered away from their universities. There's, the Bureau has done some things to try to correct for that, but yeah. There are also overcounts. Maybe your family has two homes. Both homes got a census form, and the two adults in the home didn't realize that the other one was filling it out, and so they filled it out twice in two different places. Okay, so there's a lot of error, and there are some interesting things coming out now about the noise from differential privacy being completely swamped by the errors that came from other sources. And those errors don't have such nice distributions either. But seriously, the task for all parties, both the Census Bureau and the users and the consumers of census data, is absolutely huge. People don't know how to think about numbers that have been intentionally perturbed. You can ask me more about that. I'm not going to, yeah, you should ask me more. But the hurdle to actually doing valid statistical inference in this kind of a setting is just enormous. And there's a huge effort that's needed, and it isn't done. It hasn't been finished. Though there's some very nice work that I just found from MIT recently on this kind of thing. There's intense pressure on the Bureau for numbers at very, very fine geographical levels, down to the census block, which is, census blocks can be quite small. In rural areas, they might be on the order of 50 people. Small number of hundreds maybe would be a very big block. And since census data are used for zillions of things, including determining school-age populations and, I don't know, water district consumption, all sorts of things. People are really used to having these data at a very fine level. They don't necessarily need the data at this very fine level, but that's what their off-the-shelf software has been programmed to use, or that's just how they're used to thinking about it. You can't say to them, go back, abstract the problem, and tell me what you really need. That's just not a supportable request. So there's intense pressure on the Bureau. There's also very, very scant support for privacy per se outside of the Bureau. Think about this. Everybody who's using the data is used to using the data in a very specific way. They like privacy. Privacy's cool, but they're not used to, so could you please do what you did before and give it to me the way you used to give it to me, because that's what I knew how to work with? It's totally understandable. But even civil society organizations who urged their members respond to the census, and we promise we'll do everything in our power to preserve your privacy. Even those organizations were saying to the Census Bureau, this district here, there are, you've added some noise. It's not acceptable. So it's a huge problem, and this is where we are. There's a very interesting, I said it was my last slide, I lied. There's a very nice issue of the Harvard Data Science Review that talks about a lot of these points of view. So it's a nice starting place to see what people have been thinking. But there's also a lot of new work coming up right now. Like I got 3 fascinating papers this week on this kind of thing. This really is the last slide. So this is an exciting time for differential privacy. It is pervasive in industry. It's being used in some places for California smart meter data analysis. It's being used by the IRS, the Department of Education. It's being used in classification of medical images. There are new models proposed. This is something I alluded to early on. Maybe we'll talk about something called the shuffle model in industrial use tomorrow. New amplification results, we'll definitely talk a bit about those. New techniques for bias correction of statistics on noisy data. We need a whole lot more of this. If you're interested, there's tons of work to be done here that is interesting mathematically and of great social use. There's also been some absolutely drop-dead gorgeous work on private high-dimensional median and computations that is leveraging work that was done at MIT on just general high-dimensional medians without the privacy. And then tomorrow we'll talk a little bit about applications when privacy itself is not a concern, but privacy gives you something else that's useful. And that's it. Thanks.
Any questions? What do you think the likelihood is that European courts will rule that differential privacy provides some protection against GDPR?
So I'm hard of hearing. Could somebody repeat the question to me? Somebody closer to me? What do I think the likelihood is that the Supreme Court?
The European courts will rule that differential privacy or some form of it.
Right, right.
Protection is GDPR.
Good.
Against what's the last the acronym?
The GDPR, the General Data Protection, or what? I don't know. Regulation, maybe? Okay. So this is a great question. And I don't know the answer to that. I don't know how to assign a number to it. So I actually, parts of the GDPR control the movement of data. Differential privacy gives you nothing on the movement of data. It's just an interface between the questions and the answers. So I can't answer that. But there is one incredibly interesting aspect of the GDPR. The GDPR has what's called the right to be forgotten. You can say, I don't want you to have my data anymore. You must delete my data. So I have no idea how that's going to be interpreted. Like, suppose I have published some statistic, and now somebody says, remove my data, or a bunch of people say, remove our data. Do I need to publish a new statistic or not? Unclear. But remember how differential privacy says the outcome is essentially the same, independent of whether any small number of people opt in or opt out? In a sense, it automatically gives you the right to be forgotten. So I think that that's going to be useful in considering whether it should be considered viewed as compliant with GDPR. Yeah, great question. Anything else?
I have a question as well. So you mentioned that for the census, so we have 350 million people, and I forgot how many.
7.7 billion.
7.7 billion queries are being made. So if I had access to the answers to these 7.7 billion queries done by these differential privacy algorithms, I could try to see what's the most likely population that gave this. So,
yeah.
do the results provide any sense how many queries would then make it not private?
Yes, I mean, absolutely, and that's where the power to understand cumulative privacy loss over composition comes in. So, roughly speaking, by choosing your overall global epsilon, you have controlled this completely. And you can make it small or you can make it large. If you make it small, you'll have great protection, but you might have lousy statistics. So there's a dance constantly going on. But yes, you have control.
And in the case of the census, is it known what that epsilon is?
Absolutely. So the census used, we really shouldn't get me started on this because the census used what was called concentrated differential privacy, which is this more fancy notion, which we'll talk about tomorrow. The values of the parameters that they chose correspond to a rather large, so they published what that value is, okay? I don't remember what it is, and I don't remember the translation exactly, but it corresponds to a large epsilon. Now we're just like 3 minutes on what the census does. If you're used to abstracting things, you're going to, like, your hair will go up here and you'll want to run screaming from the room. There was legacy software at the Bureau. There are regulations about what is the official count. The official count is what happens when you feed in records of people's responses to a specific tabulation algorithm, which then does some counting in a very natural way, and it produces outcomes. So what did the Bureau do? They said, we have to create synthetic people in a privacy-preserving way. So this is okay. This has been studied. How do you do synthetic private data? However, they decided that they would keep the state totals intact without any noise on the state total population. That was a political decision because they had to, because apportionment is done based on those numbers, and they didn't want to have any arguments about those numbers. So, okay, the states and Puerto Rico and DC, we're going to give those numbers exactly. They also, they had to create synthetic people. You can't have negative people. So think about a really small district, a really small census block. And let's say that you're counting the number of people in this census block who have self-identified simultaneously as Asian, black, and white. So maybe there is 0 in this census block. When you add noise, symmetric noise, you'll get a 50-50 chance of a negative number. We can't have negative numbers. We can't have negative people. So they took those negative numbers and they said all those negative numbers are 0. Then they did a maximum likelihood reconstruction using a solver to find a data set of sort of synthetic people that as closely as possible matched those numbers. Now, remember I said you kept the population total fixed? And there were negative numbers here. So they ended up sort of moving people from urban centers, virtual people from urban centers off to these sort of empty districts in order to get the totals non-negative. So that's called the post-processing phase. They took noisy counts in a real differentially private way. They post-processed using this horrible mechanism, which destroyed a lot of information, and that's what they published. I hope, in fact, we wrote a letter that was published in the Globe. We said, give us the noisy measurements file, right? But I don't think we're going to get that. And I think it's possible that we're not going to get that because the privacy parameters they used were so large. And so, yeah.
Any other questions?
Yeah.
Is there some behavior scientists and studies that estimate what fraction of people, say, would have not responded and are told that it's differently private?
So if I heard you correctly, you're asking, was anybody persuaded to respond because privacy was being offered to them? I think nobody had differential privacy explained to them. However, I did mention the civil society groups who were encouraging people to respond so as, to count the Mexican American population and so I really believe that they promised to do everything in their power to protect privacy. I think that could have well been persuasive. So I think people care about privacy. I think vulnerable populations care even more about privacy. But I don't think anybody had DP explained to them. I mean, the Bureau makes all sorts of stuff public, including that, and they have videos on it. But in fact, there's a wonderful one by the guy who does, there's a wonderful one which reminds me, I'm not sure it's the same person, of the KDD cartoons. Who sees it, I don't know. Let's see, there was you, and then here. Loud.
You said something about how people have trouble doing statistics with noisy data.
Yeah.
But so why is this different? Or why do people think about it differently than if they were just doing classical statistics where they're looking at data?
So what's the question? So
you said to ask me more about people have trouble dealing with statistics that they know noise is added to. People have trouble dealing with statistics that they know noise has been added to.
right.
And I'm confused with how is that different from, well, there may have been noise from classical statistics.
Good. So if you know what noise has been, the way in which noise has been added, you're in much better shape for doing statistics. what is quite interesting is that I can't find much at all in the literature about statistical inference with the kinds of sources of errors that predated differential privacy. So doing statistical inference with missing data and biased data is difficult. And so the anthropologist Dana Boyd has together with Jayshree Sarati, a student at Harvard, has a very interesting paper about what they call statistical imaginaries. And one of the things that they talk about is how there was a fiction that the numbers that the Bureau was reporting were the exact numbers. And it was like a compact. Everybody had agreed they were going to pretend those were the true numbers, and they were just going to do statistics as if those were the true numbers. And when differential privacy came along and the Bureau said, we are perturbing these things, there was a lot of shrieking, and people objected. But it's more a question of seeing how the sausage is made. And there's, I think, still a disconnect between understanding that what was done in the past was also, had problems, especially because nobody was doing the statistical work that they needed to do in order to correct for the kinds of skewing of the actual census responses. Okay. Yeah. Oh, sorry.
Quick question. I was just going to ask, I mean, kind of related to Michelle's question of, like, if the epsilons are really large, also for, like, Apple and Google and stuff, like, to what extent is privacy actually being preserved?
I don't like epsilon being large. I'm not comfortable with it. That's the best answer I can give you. I don't think it's a good idea. I don't think it's preserving meaningful privacy.
Okay, let's thank Cynthia.
Thank you so much, Michelle, for that very, very gracious and informed introduction. I really appreciate it. You can all hear me? Great. Okay. So the first two lectures will be about differential privacy. Today's lecture is really intended for a very broad audience, and I will point at a few different things that we will go into in more depth tomorrow. Yes. Good. So the title for this series is Mathematics and Mores, and just for the non-native speakers, I wanted to just give the definition of mores as the fixed morally binding customs of a particular group. Notice that it doesn't say what is right and what is wrong. It's not the same thing as ethics, but it's contextual. And that will be particularly important when we get to fairness. This is part of a theme for me. I really, really believe that theoretical computer science can be a vector for positive societal change. And I think that all of us could work in that direction. So let me say a little bit about privacy in a nutshell. When we think about privacy-preserving data analysis, there sort of are two kinds of things that we might think of. One of them is somehow the statistical understanding of the population as a whole. For example, as we do with the census data, or as we might do if we're trying to analyze the history of loans, looking for evidence of discrimination, or even coming up in machine learning where we're trying to train